Good day to you all. Evan Stamon here for 1.12 Making a Difference. Okay, we are now going to start actually looking at the grade 12 content, which is the formula for a circle, and it is the analytical idea of a circle. What I'd like to go a step back to quickly is the idea of a circle according to, I don't know, perhaps a bit more of a geometrical nature. And that is perhaps a guy standing in a field with a string, and on this end of the string is perhaps a weight, and he is swinging this weight around. And if you think it through, this string with a weight on it is going to come around, and we know that no matter what happens, and I know my drawing's not the world's best, but we know that the distance from his hand out to the stone or out to the weight is always going to be the same distance. Now it is that idea that I'd like to try and pull out to look at in terms of a circle's definition at the moment. The idea that a circle is the range of points that are always equidistant from a circle center. Okay, so what I need to do to take this further is the idea also then of looking at some definitions coming out of the idea from the topic of functions. When I had y equals, for example, 3x plus 5, we saw that the power on the y was a 1 and the power on the x was a 1. And we saw that when we looked at the graph of this thing, that this thing would have been a straight line doing something like this. I'm not so fussed about the values or the accuracy of the graph. What I am interested in the fact is that there is a single y-cut. There's only one y-cut. And there is a single x-cut. Okay. When I had the function, for example, y equals x squared minus 9, we saw that this function did the following. We saw that it had that shape, but what I want to look at more importantly is the fact that this thing had one y-cut, but it actually had two x-cuts. Okay. Now, what I've always had as my thesis is that if these ideas, the equation and the graph, represent the same information, isn't there something in the equation that shows this notion of the number of cuts? And I'd like to point out to you that there actually is. Maybe you've seen it before, maybe you haven't, but the fact is that the y thing still has a power of 1, and that links to this idea of the single y-cut. The x value with a power of 2 links to this idea of the two x-cuts. Now, it's not to say that there will be two x-cuts. Those of you who have played with the graph of x squared plus 9 know that this thing does not have any x-cuts. But the point is that it has a maximum of two x-cuts. There is at least some link, some tension, some connection between the highest power on the x's and the number of x-cuts, and the highest power on the y's and the number of y-cuts. Now, what this leads us to understand is, if I was to now consider what would happen if I drew a perfect circle, and again, this is not my favorite drawing platform, so let's have a look at it. I will be getting something that does roughly that. What you might notice is that it has two x-cuts, and it has got two y-cuts. This should not surprise you then, that if you buy into what I'm saying with the idea of functions, that what this means is that it's not too much of a stretch of imagination to see that this thing's formula will be x squared plus y squared equals r squared. Now, the x squared, again, is telling you that there will be two x-cuts, and the y squared is informing you that we can expect a maximum of two y-cuts. Again, it's not to say that there will be two y-cuts, to say that that is the maximum, but there is this, again, connection between these two ideas. Now, again, this is coming from the functions. However, I would like to look at it from a slightly different perspective again, from our definition we were looking at just now. If we had this idea of a rope, and this rope was attached to a weight, and so we said that this rope was equal to, I don't know, let's say 5 units. Okay? And we were sitting here, and the center of the rope, the person who's holding the rope, that was at the origin. Then what we get is a situation where every point on this rope, something slightly better circle than I drew just now in blue, that every point on this dotted black line would have a distance from the origin of 5. So if this point was x and y, we know that the distance formula says that the distance must be 5. So if the distance is x1 minus x2 squared plus y1 minus y2 squared, then we are saying that 5 equals the square root of 0 minus x squared plus 0 minus y squared. So 25, squaring both sides to get rid of the square root sign, would equal x squared plus y squared, which very much looks like it is the same sort of idea as we had over here at the top of the page in red. Okay, so 5 squared equals x squared plus y squared. This is very easy to understand, or not maybe very easy to understand, but quite easy to understand when our circle is centered on the origin. However, we have seen in other functions that we shift left and right. There's a component that there's a component shift, or there's a variable that changes in the function. And so again, it is not the world's, again, my apologies, just trying to get the mouse to work. If we had a hyperbola centered on, sorry, let's just quickly do that. If we had a hyperbola that was centered on the axes, this would have been y equals k over x. But we know that we shifted this thing across and we put in a set of asymptotes, let's say over here at p, and let's put this one, make this one negative, and at q, we know that actually what we've got here is y minus q equals k over x minus p. So again, a horizontal and a vertical shift are created by inserting these values of p and q onto the y value for a horizontal shift, and onto the x, I've changed that. Okay, onto the horizontal shift and onto the y value for a vertical shift. Let's see if I can get it in. Okay, so the y value affects the vertical and the x value affects the horizontal. Again, if we understand this, then it is not too much of a stretch to understand that if a circle is centered at the origin, it is going to be x squared plus y squared equals r squared. Effectively, the same as saying x plus 0 squared is the same as plus y plus 0 squared equals r squared. That if I was to shift this graph to a new center, that I would now get x minus p squared plus y minus q squared equals r squared. So if it was now centered at p and q. So what we now have is our full formula for a circle, which is x minus p squared plus y minus q squared equals r squared. And again, that is simply a more complete version of x squared plus y squared equals r squared. If it is centered at the origin, and if it is centered off the origin, x squared plus x minus p squared plus y minus q squared equals r squared, where r is the radius of our circle. So to be centered thing, and our radius will be r. Again, just want to quickly put that in the notes so that it is clear. And the radius is r. Okay, so we're moving quite swiftly here, and we can look at now a couple of easy questions. For each circle, identify its center and its radius. Again, we are suggesting that the formula we are interested in is x minus p squared plus y minus q squared equals r squared. So if we apply that here, x minus p squared, well, that implies that p is minus 2, not positive 2. And if you look at y minus q squared, we can see that q is going to be 5, positive 5, not negative 5. And if we buy into the idea that the 36 is in the position of an r squared, then we can see that r will be 6. So that tells us that the circle center will be at minus 2 and 5, and that its radius will be 6. And again, that is sufficient information with which to draw it. Okay, I would know that my circle center would be at minus 2 on the x-axis, 5 on the y-axis, and my circle would go 6 units up, 6 units left, 6 units right, 6 units down, and somewhere here, oh, it's very bad drawing, so let me just undo that. Okay, and somewhere here would be my circle. Minus 2 and 5 with a radius of 6. Now, we're already doing the second part of the lesson where sketching functions is coming into it. Okay, so again, we need to be able to sketch the function, and knowing its circle center and the radius is sufficient to be able to sketch the function. Okay, so we want to do the same thing. If it worked once, we're going to do it again. This time around, they're trying to trick us a little bit. So that is in the position of x minus p squared. It is so simple because they're hiding away the p, so p equals 0. They've put a 9 in here to see if they can confuse us with the squaring, but we shouldn't be confused by it. Y minus q squared, which means that q is 9, and in this case we've got that r squared equals 18, so r would equal 3 root 2, which is approximately equal to 4.7. Okay, people got it right. Yep. Perhaps a bit generous, but let's leave it at that for the moment. Okay, 4.2, 4.3. Okay, cool. So again, sketching this thing, we know it's going to be centered at 0 and 9. So 0 on the x-axis, 9 on the y-axis. So over there at 0 and 9. And again, knowing that the radius is approximately 4 and a bit, and knowing that the height, that the center is 9 units up, means that I know that this circle is not going to cut through the x-axis in this case. It's only going to be above the x-axis because the radius is shorter than the 9. So r equals root 18, or 3 root 2, or 4.3. Okay, so identifying the circle center and its radius allows us to sketch the graph, and we can sketch the graph very, very quickly. The key thing is to be able to take heed of its features. Okay, so again, what we need to be able to do for our function, our topic here in grade 12, is we need to be able to do one of 3 things. Okay, so when it comes to circles, as with any functions, we need to be able to get from the equation to the graph using a sketch. We need to be able to get from the, sorry, I'll fix that. We need to be able to get from the graph back to the equation. Okay, and 3, we need to be able to get, if we're given both the graph and the equation, we need to be able to identify the features of the function. Okay, so what I'd like to do now is to look at the next slide. Okay, graph the following circle. Again, not overly difficult. We can see that the circle center, okay, that's a symbol for circle center. The circle center is going to be 1 and 3. We can see that the radius is going to be 2. Again, not difficult. 1 across, 3 up. There we are at 1 and 3. The radius of 2 means it's going to go 2 to the left, 2 to the right, 2 up, 2 down. And I know this is not my best circle, but it's a sketch, and there we go. There we have it. Our notion of a circle, 2 to the left, 2 up, 2 down, 2 to the right, etc. Okay, you don't need to use a compass. You could take in a bottle top, I suppose, if you wanted to. You could have anything in your stationery bag that is round. That might be a easy way to draw circles. But it is a sketch, not a drawing, so it just can't be too raggedy or too uneven. What I'd now like to look at is what happens if the function is not given to me in that nice standard form. So if I gave you x squared plus 4x plus y squared minus 6y equals, I don't know, let's go for it, let's say 12. Okay? Now, remember, the standard form is x minus p squared. So I would like to get the x components to have that format of x minus p squared. That would be ideal. It then goes plus y minus q squared. So again, I would like that second part there, with the part involving y's, to be y minus q squared. Okay? And so what I need to do here is do some thinking, and this is going to equal r squared. So again, we're going to do a topic which, again, you're going to get very familiar with if you continue with this chapter, and that is to complete the square. Now, to complete the square, there was a little trick that you learned back in grade 11, which was that you take this value here, as long as this coefficient is 1, you take this middle component here, the 4, and you halve it and you square it. So what I'm going to get is x squared plus 4x plus a 4. Sorry, I want to quickly, okay, plus a 4. And this 4, I'm going to come back to, and I'm going to get plus y squared minus 6y. Same trick. If a trick works once, you may as well try it twice. X squared minus 6y, half the minus 6 is minus 3. Square the minus 3, and you're going to get plus 9. Okay, so you've done that. Okay, and that's going to equal the 12. But again, what you do to one side, you must do to the other side. So I must add 4 equally much to the left-hand side as to the right-hand side. I must add a 9 equally much to the left-hand side as to the right-hand side. So I get the following. Now, please don't forget the reason you did this. You did this such that this would form the required perfect square. Now, this is going to be x plus 2 squared. And again, you did this step for the same reason to get a perfect square. This is going to be y minus 3 squared. If I've done this correctly, 12 and 4 and 9 adds up to 25, which is a nice value because it is a perfect square. It doesn't always have to be a perfect square. We've seen that in previous examples. And so I'm seeing here that the circle center will be minus 2 and 3. and that the radius will be 5. And sketching it now is no, as we've seen before, is not actually a big deal. It's going to be at -2 and 3. There's the circle center at -2 and 3, and my circle has a radius of 5, so it's going to come through here somewhere. I know it's a bit egg-shaped, and I apologize for that, but that is how I would go about completing the square to change a non-standard form of the circle equation into the circle equation, identifying the P and the Q values as well as the R value that I need for the radius, and I now can draw or sketch my graph equally easy. Okay, again, thank you for your time. Hope you had a good one. See you soon.